All right, here's my clever title of Ice and Men. Thank you very much. Before I actually get into my experiment, I have a quick little intro video for everybody.
Oh, is this X-rated?
Thanks, Ice. You're so refreshing.
That's creepy.
The ice melted. Son of
This models my experiment in that the situation that I displayed to you I'll exaggerate greatly. If we were to like that. Personally, whenever I work on stuff, I like to have me a cup of ice water. And more often than not, I'll reach over for my ice water and my ice is gone, and that's frustrating to me. So this brought to mind a couple of questions I had. How long does it take for ice to melt? And can we choose the best ice? So this brings me to my experiment. I just wanted to compare the rate of time of melting of different sized blocks of ice. And to do my experiment, obviously I need some steps to take. And my very first step would be to obtain equipment. Graduated cylinder, this one measures 100 milliliters. You also need a stopwatch. And you need some bags to hold your water, all the same Ziploc bags. I have 9. I use 9, there's just a couple that I use. And also you have to label them. For that you can use a marker. And our next step will be to fill the bags with water using a graduated cylinder. Fill them up. And the reason I have all the identical bags is because when I stick them in the freezer in the next step, you want them to, well, they'll freeze, obviously they're all freeze, but during the following step, melting, you want them to melt under the same conditions. We're trying to narrow our variables, and to limit the number of variables we have, we use the same bags. Fifth step, record data. And for that, that was the inquiry design lesson plan I had. That has the table for us to record the data. And our final step will be to analyze, and I'll get to that later. I have another video for that. That's funny, sorry. But like any good scientist, before we do our experiment, we need to form our hypotheses. And my null hypothesis is that the rates of time of melting for the different blocks of ice will be the same. And my alternate hypothesis is that the rates will be different. And for my measurements, I have my independent and dependent variables. My independent, because I control it, were the size of the blocks of ice. I had 3 50 milliliter blocks, 3 100 and 3 200. This is 1 200. And my dependent variable was time, because the time of melt, the time to melt depends on the size of the blocks of ice. Almost choked. And this was after I froze all my bags, and I got them out and I laid them out in our spare room in my house. And it's kind of hard to see because I took the picture on my cell phone, but here I have my 3 50 milliliter, 100, 200. And it wasn't quite as boring as Katie's. It took a long time for these all to melt, but I didn't spend my whole time just... If you want a video of me, or of the ice melting, then just imagine this picture, because it's about as exciting as it got. Now for some results. It took in the ballpark of 2 hours for the 50 milliliter block to melt. And it was a very long 2 hours. For the 100 milliliter block, it took about 3 hours. And for the 200 milliliter blocks, it was in the range of 6 hours. No, I didn't sit there and watch it. Y'all are looking at me like I would sit here and just, that I didn't do that. I was running back and forth doing things. But this block was different. And when I was not watching, but when I was taking notes on the melting, I looked at that block and I noticed, well, first, if I pour water in here, in this bag, what shape is it going to make? Just imagine if I pour water, it's going to fill up, and at the bottom it's going to be what kind of a triangular prism, right? It's going to be, it's not a cylinder, I don't know. And for the second 200 milliliter block, it was the same shape. See if I can draw this. But right in this area was kind of an air bubble. And this is as good as drawings I can make. But the air bubble was the reason I think that time was quite a bit less than the others. And once I had my results, obviously the next step would be to analyze. So I have this is a 7.5 minute video, so buckle your seatbelts. And this is, oh my God. But this is showing you how I analyze, as well as for those less experienced with Excel, this is a good learning tool. It's also uploaded to YouTube.
All right, we're going to learn how to make a graph in Excel. And the data we're going to use is the data I've gathered in my ice melting experiment. First thing we need to do, obviously, is to open up Excel. There we go, and we get a blank spreadsheet. And our next step will be to enter our data. Now in the left-hand column, we're going to put our independent data. And for us, that is the amount of ice in each bag in milliliters. Okay. And then the right-hand column, we're going to put our dependent data. And that is our time in seconds. And we're going to expand these columns just by clicking and dragging. Okay. Now in the A column, we're going to enter in our dependent data sets. And so we had 3 50 milliliter bags, 3 100, and 3 200. Okay. Now the B column, we'll enter in all of our corresponding data. And just to speed up the process, I already have this data copied, so I'm going to paste it in like that. Okay. Now we have everything we need to make the graph. What we're going to do is we're going to click in the top left corner, and then we're going to drag all the way down. So now we have everything we need highlighted. We're going to click Insert, and here we have our choices for all the graphs and plots we can use. And the one we want to pick is our scatter plot. We're going to use just the basic scatter plot. Click on that, and there we go. Just down here. And the first thing we want to do, there we go, is we want to edit our title so that it reads as dependent variable, in our case time, versus independent variable, amount. Okay. Now we want to add our axes labels. Excel doesn't do that automatically, so we need to go in and do that on our own. And up here on Chart Tools, we have to make sure our graph is selected, otherwise this won't show up. And to know that it's selected, when we click on it, we'll see both a border around it and the Chart Tools menu will show up. And once it's selected, to add our axis titles, we're going to click Layout and then Axis Titles. And for our horizontal or our x-axis, we're going to hover over a horizontal axis and then put title axis below. And then we'll have amount in milliliters. And we'll do the same thing for our vertical or our y-axis. We're going to select rotated title. And this will be time in seconds. Okay. Now our next step is to add a trend line. So again, we're going to stay on layout, and here we can see trend line, more trend line options. And we can pick from exponential, logarithmic, so on and so forth. But just looking at our data points, we can see that the relationship appears to be linear. So we're just going to leave linear selected. Then we're going to come down here and we're going to click the boxes to display our equation and to display the r-squared value. And then we'll click close. And here we have our equation, r-squared value. Move them over so you can see them. And the r-squared value, if you don't know, it tells you how well your trend line fits the data. And as you can see, we have a 0.99 r-squared value. And that means that our trend line is a very, very good fit for our data.
I'm going to pause it there. When I got my trend line, at first I was okay with it. And then I looked at it for a second. And I was thinking something is wrong about this in the context of the problem. As an equation, it's a perfectly okay equation, just basically your equation. But what does this equation tell us for a 0 milliliter block of ice?
gonna take it a while to melt.
For a 0 milliliter, how many seconds?
I can't see the equation.
Oh,
3,000.
3,000 seconds. Does that make any sense? Here I have a 0 milliliter block of ice in my hand. How many seconds?
3,000.
That doesn't make any sense in the context of a real life situation. So I thought about this, and I talked with Leanne and Amar, and I studied chemistry or physics or whatever it was. and they helped me realize something. It was pretty neat. And it has to do with the phase. Shoot, marker. Can y'all see this marker already?
Yeah.
Oh, I hope you can. And it has to do with the phase state changes and the energy that deals with these phase state changes. When I took the ice out of the freezer, the energy being added to the ice from the warmer air surrounding it, the energy goes to the ice. It increases the temperature. It'll be in Celsius. So the temperature increases from whatever my freezer temperature was to 0 degrees. And it gets to this point, and all's well with the world. But once the ice reaches 0 degrees Celsius, the temperature quits changing. And when they told me about this, mind was blown. I was like, what? So I researched and I realized that the time, from the time you take it out of the freezer to the time the ice reaches 0 degrees, was my 3,000 seconds. So that accounts for the y-intercept here, which was throwing me for a big loop, because I saw it and I was like, my equation can't be right, but it has to be because it fits the data so well. And the video goes on and it shows you how I make my other graph, which I will skip that part. Here's my time graph. And this point right here, as you can see, is the oddball piece of ice that I had that didn't want to hang out with the rest of the ducks. Here's the other graph that I made, and it has to do, it plots the rate of time versus the amount of ice. And this was the big controversy when I was introducing my experiment however many classes ago, and I wasn't understanding the question, so I'll take all the blame for that. And my rate of time is seconds over milliliters. So just looking at this graph as is, which amount melts the quickest? Just
200.
you all are saying that you said the 200?
Mhm.
Does it seem like the 50?
Yeah, that's what I was gonna say. The 50 would
It's
melt
the higher
faster
rate of
because of the
melting.
higher rate of melting.
Yeah, it's the higher rate of melting.
But that's seconds per milliliter.
The highest rate of melting would be quicker, right?
Exactly wrong. and instead of explaining to you, I have a little activity, and I have 3 volunteers. Stephen, you volunteer. Jess, you volunteer. Who's my third volunteer? Thank you. Oh, sorry, she got you first. Okay, I'll come on up here. Okay, Stephen, I want you to stand on right here. And then Courtney, I want you to stand in the middle. Just sure this works, you stand over here. Now I want you all to hold your fist up like you're going to punch me in the face. Now here's what I'm going to do. Now you're not actually going to punch me, Stephen. Relax. But you can hold your arms. Don't clench your fist. It makes me nervous.
No.
Okay. Now, what I'm going to do is I'm just going to start counting. And when I hit a multiple of 2, I want you to tally that by just going, boop. When I hit a multiple of 4, you're going to go, boop. And when I hit a multiple of 6, 6, 12, 18, boop. Okay. Now, before I go, I want us to think about what this experiment, or what this little activity, how this relates to my graph. What does my counting represent?
Time.
Time. What do the tallies represent?
Melting.
The melting. It's how many, in the context of the ice, it's how many drops are melting, okay? Stephen is representing the big block because he has if you look, this rate is close to 90, the smallest number. Every 90 seconds, 1 milliliter drops, okay? So Stephen is the big block, Courtney is the middle, Jess is the teeny tiny block. So I'm just gonna start counting. Stephen multiples of 2, Courtney multiples of 4, Jess multiples of 6. Ready? This up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Jess, did you keep up? Okay, good. How many drops of water did Stephen lose?
10.
Courtney?
5.
And Jess lost
3.
3. So if they were blocks of ice, who melted the fastest? Stephen melted the fastest, not Jess. Our big block is melting the fastest. The reason for the confusion is because we're looking at seconds over milliliters. We're used to seeing things as miles per hour. If I have a larger miles per hour, y'all can sit down. Y'all can feel weird. If I have a greater miles per hour, obviously I'm traveling faster than somebody with a lower. But my units, your perception was kind of messed up. So here we saw that Stephen melted the fastest. Or in the context of ice, my big blocks melted the fastest. However, if we look at our previous graph, the small blocks finish melting first. And that's because they're smaller, there's less to melt. And we come full circuit back to our hypotheses. I reject my null hypotheses, obviously, because the rates are different, clearly. Also, before I continue, I have an Excel chart. Instead of doing that little activity, I could have just shown you my Excel chart that I used to calculate. Ooh, that is very small, isn't it? Here's my seconds per milliliter. The small block has the largest seconds per milliliter. But then we look at rate as something we're familiar with, like miles per hour. This is milliliters per second. You can tell that the big block had the largest rate, melted the fastest. Lost the most milliliters of water per second. Go back.
Well, you said you lost the most amount of milliliters per second, to whereas you had it written, had the most seconds between milliliters lost is what it should be read as. Am I correct? Or we can just say that for the question's sake?
I'm not sure. Save that, and I need to think about what you're saying, because I'm in presentation mode, sorry.
Yes, I'm sorry. Didn't really ruin your mojo.
Oh, I rejected my null hypothesis. The rates are different, and even for my milliliters per second rates, those are different as well. And as far as things that would affect the rates and how the ice melted and things like that, the biggest problem I had was that when I hung these up, I hung them up in my freezer. Like they were across in a row. They were hanging like this, so some of the blocks were touching. And that could cause maybe the shapes of the ice to be a little different, and that could have some kind of minimal, negligible effect. And the biggest problem I had would be this block. It was just this one block, and I don't know why, but it had just this little indentation, and it was kind of an air bubble, and the increased surface area caused it to melt faster than its compadres. Finally, we come back to my second question: which ice is the best to choose? I don't know. It's totally arbitrary. I talked to Leanne and Amar yesterday, and Leanne said when she goes hiking, she likes the big pieces of ice because they last the longest. Amar said he likes the little crushed sonic ice because it melts the least. He was never know with Amar, but it's totally arbitrary. Whichever ice you prefer, you can't really make any definitive choice. It depends on if you're hiking or if you have a little drink. Now, Robert, please run the mojo.
Can you go back to your, let's go to the slide that you have the means, or the rate of change. Go to that. This was slide 13. Yes. Or 13. 15, sorry, 15. You said it was milliliters per second. to where it's seconds per milliliter.
This is seconds per milliliter.
Yeah.
I also calculated, I had milliliters per second. In my
Oh,
Excel
okay.
file.
Okay. Sorry.
This would be seconds between milliliters.
Sure.
Yeah.
You report your melting times down to the very second. Are you that accurate with your data to say that a 200 block of ice actually melts like 18,417 seconds?
That was the timer I put on the stopwatch, but I could have very well rounded. It wouldn't affect anything.
But I mean, were you
The
accurate
times
down
are
to
so
the
bright
second?
that such a small change isn't affecting a whole lot of anything.
Okay, I just thought it was strange that you would round it to the nearest
And
second.
in case you're wondering, I was in the room staring at ice. It's as exciting as it sounds. It's like this. Paint's drying awful nicely today. That was my weekend.
So you hit.
Don't make fun of your home, Tracy.
I'm gonna ask a simple question,
Thank you.
because I don't want anybody asking me questions in front of me. To me, logically, if I've got a large piece of ice, and maybe I'm misunderstanding what you're saying about the rate. If I have a large piece of ice, I've got more surface area, so I'm going to have more drops per second.
And it is melting faster.
So
Steven
does
was
that
melting
mean that
faster
my
than Courtney.
rate is faster? Or does that mean that I've just got more melting occurring? You see the difference that I'm trying to, does that make sense?
Does the
I'm
rate
wrong?
change over the time, I guess is
Oh,
the
okay.
question.
One of the assumptions I made was that they melt at the same rate throughout. Because I mean, I virtually had no way to see if it was melting. I mean, honestly, I didn't want to sit and stare at ice for 6 hours and measure maybe on hour intervals to try to calculate the rate.
Right.
So I just assumed for the full 6
Okay.
hours, I said same rate. Just to simplify. If you wanted to somehow adapt this to use in a classroom, you don't want to mess with students and say, well, I'll let you measure this every hour and determine the rate by pouring the water out and calculating.
Right.
I was wondering, if you had like one big 200 milliliter block and you had a bunch of like 4 50 milliliter blocks packed together in one bag, do you think they would have melted at the same rate, or do you think they would have changed?
Probably would have been faster with the air.
I don't know. In my head, I feel like it's getting into a lot of physics as far as having the ice touch, and that eliminates a lot of the surface area. So maybe it depends on how they're stacked. Like if you had big block, little, if you had big block, little, just, and it's dealing with the surface area of the ice, and that's beyond anything I feel confident enough to talk about.
Did you enjoy making that video at
No.
1:57 in the morning?
Oh, you noticed! I'm so proud. Thank you so
You're
much.
welcome.
I appreciate it. I was waiting. I told Leanne, I was like, somebody's gonna notice this. She said Robert was going to. I was like, no, he's.
Why did I get thrown into that?
He was saying that you were,
Hey.
he was basically saying you were observant, and then,
That's exactly
Ah,
right.
dang.
but Leanne said, no, you're not observant.
I know why you chose to do what you did there, because you had times and you had milliliters. And I really do think it's good for students to see both ways. Now, if you just think about that, normally we don't talk about seconds per milliliter, we talk about milliliters per second. And I think how would you convert those, everybody, to milliliters per second?
What'd you say?
Those numbers right now are seconds per milliliter. If you wanted milliliters per second, how would you convert them?
Take the inverse.
Okay, give me a better name for the inverse for a sixth grader.
1 over,
So give me a big long word that starts with an R. So all you have to do is put that number in your calculator, hit the 1 over xt, and you've got it. And I think, Tracy, that was part of the deal there was, if you consider those numbers as 3, 2, and 1, the reciprocals would have been 1/3, 1/2, 1. You would have seen right away which one melted the fastest. So I do like that you do that. The biggest attaboy I want to give you on that, and I hope to encourage you all the same thing. Imagine that he's trying to explain in class how to do this on Excel, and you've got 4 people absent. Or imagine he's got to give that same explanation 5 times that day. Take the time to make a little video like that, play it in class for that 7 minutes for them to see how to do it. And then when they say, I still don't understand, or I didn't catch all the steps, it's on YouTube.
The video is on YouTube,
Go pick
and
it
the
up.
rest of the video I'll show you how to make this graph, how to translate some functions into cells and stuff like that. It's nothing too fancy, but it's crucial if you want to be efficient with using Excel.
But
So you can find that.
it really will help you, you know, as you teach longer, some little procedural things like that you can do a little 2, 3, 4 minute instructional video and store them on an EDU 2.0 type environment. Then, you know, when parents are calling saying, my child's, well, it's online, and kids love to get on the computer. So there you go. Good job.